Yeah, being in the Midwest, compared with the rest of the United States, but also in part of the world, we through our corn and soybeans, we're able to grow a higher density of materials than most parts of the rest of the world. The other parts of the world that are very advantageous for high density materials, it would be feedstock for forest products or for vegetable oils would be, as an example, Brazil or parts of Indonesia and Malaysia in Southeast Asia. So there's a unique opportunity that we have here in the United States, but also in the Midwest, in using biomaterials to develop for use in what I would basically say is the specialty chemicals industry. Okay? And we like to talk about our materials as being biomaterials, but all we're doing is synthetically, if you will, taking these different molecules from various sources and engineering them for beneficial use, in our case, for use in asphalt materials. And so it's not like we're going out and coincidentally saying, hey, I wonder if this juice or this flavor will work in asphalt. That's not what we're about, and that's not what we're doing. We're looking at these different materials and trying to understand the molecules and how they could be used beneficially in asphalt, or if the price point looks reasonable, how we could improve those molecules through a one or two-step process to evolve those new molecules to better molecules for use in asphalt materials. Okay? So what I'm going to focus on today is our development of renewable polymers for use in asphalt pavements. I'll give a little bit of an overview on some of the biomaterials, and then we'll go into some of the work that we have been doing in the biopolymers area. It's important to recognize that, yes, I'm kind of one of the lead people with Ashley Buss in the asphalt materials area at Iowa State, but this is a very, very comprehensive set of people involved with this. At any one time, it involves 30 to 40 people from a wide range of departments, not only in civil engineering, but chemical and biological engineering, ag engineering, chemistry, in fact, statistics, and a lot of other areas. So it's a really interdisciplinary, cross-disciplinary effort going on here at Iowa State. And so I think it's important to recognize that I'm speaking today on behalf of a broad group of people, basically. Well, before we get into this, the challenge that we have with these types of technologies are we get an idea, we got to stay with it, we got to dog it and work it until it's done right, okay? And someone really famous in American history quoted this, and this was Walt Disney, okay? And you think of all the things that have evolved from Walt Disney's creative aspects and animation and things that have evolved over the years because of what Walt Disney began. So we didn't go into this endeavor with biomaterials lighthearted, if you will. We saw that there was a substantial amount of opportunity. That was not just an opportunity for us as researchers, but there's a substantial economic opportunity and it's a substantial economic and social opportunity for the United States, creating jobs, developing the economy, and developing revenue. National strategic defense issues in terms of we are developing the materials here. We're not dependent upon these things coming from other countries per se. All right, so we have. I mean, this is conservative. Just in my interaction with the people in chemical engineering and ourselves in civil engineering, over 150,000 hours of research in the biopolymers and counting. Okay? So this is not something that's casual. This is something that we are living and breathing and doing every day with lots of people. Okay? All right. If we look at the overview of biomaterials, we have to look at different sources of biomaterials. We're very familiar with biomaterials that come from forest products industry. Whether that's things from Longevity, Arizona Chemical, or others, we're using tall oil products or materials from tall oil in the asphalt paving industry today, and we have been for many, many years. We also use materials from the biofuels industry. Some of the things that are indirect as an example, as biofuels. We use them in the trucking. We use them in plant operations and production of our asphalt mixes. All right, but we also have the ability to use these materials if we engineer them correctly with the right characteristics, compatibility to be beneficial in asphalt materials as well. We can also look at intermediate and/or residuals from biorefineries. Sometimes what we find in these biorefineries, they're focused in on producing fuels, okay? And they may get, let's say, some distillation bottoms. But those molecules in the distillation bottoms, they're paying, a certain amount of money to haul those materials and landfill them. But we can take those molecules in a one-step process, improve them, and create value there. And we've done this for a company where we reduced the amount of material going to the landfill by about 90%, okay? And it was because we were able to take what they didn't understand had a molecule that was beneficial, and we could make that molecule evolve to a better molecule economically and create some value there, okay? Then, we also have to be cognizant of this, fuel versus food issue that goes on in Washington, D.C. primarily. But there's far more vegetable oils that are produced that are non-food source than are the actual oil that's used for food. And when we really start looking at what is coming from the vegetable feedstock that's used for food, it's actually the beans that are crushed or the corn, and those are sources that are fed to animals, and then those animals, of course, are harvested for various use in the food industry. Okay, so we have to be aware that just because somebody casually wants to state food versus fuel or whatnot, that doesn't mean it's true. And we take the opportunity to try to educate people on these things. All right. So when we look at these different biomaterials, it's really, it's not because it's green, okay? It's because we need to have, either it needs to be cost advantaged, or it needs to be performance advantaged, or preferably both cost and performance advantaged, okay? And when we look at, this is my words, but if we look at where we are in the refining industry, we're probably circa 1930s in terms of where the crude petroleum industry is, okay? So if we look at some of the polymers, that we now use substantially in asphalt materials, those polymers were developed in the 1970s, okay? So here we are nearly, almost 40 years later in some cases, where we have common acceptance of these polymers in the asphalt industry. But it took probably 15 years before those polymers really got broad use in the early 90s, and that was part of the evolution and implementation of the Strategic Highway Research Program, what we know today as SuperPave. Okay, so when we look at these different materials in terms of opportunities, biomaterials, there exists opportunities in terms of asphalt extenders, asphalt partial or full replacement. We've done stuff that demonstrates that we can do this with our bio oil. Clearly, Evotherm is a warm mix asphalt technology, or compaction aid. We can use stuff that's a reflux or a rejuvenator. And I want to point out the important difference between a flux and a rejuvenator. A flux is a softening agent, okay? So it takes a stiff asphalt and makes it softer, okay? But more or less, there's really not chemistry that's occurring when we add a soft material to the hard material, whereas the rejuvenator is facilitating some chemistry, and chemistry is occurring so that the net result is the asphalt product, if you will, with the rejuvenator is softer, okay? And so sometimes we want to throw fluxes and rejuvenators around and pool them together, but I think there needs to be a more clear distinction between those two, okay? And then we can get to polymers, okay? So we've been working hard on a lot of these different areas here at Iowa State, but I'm going to focus my attention more on the polymers moving forward here. So let's talk biopolymers. In biopolymers, we have to first start with a feedstock of a material. In this case, we are using soybean oil. And we take that soybean oil and we have to epoxidize it, and so we create ring openings, and then we treat it with acrylic acid. So we have acrylated epoxidized soybean oil, what we refer to as ASO. All right, but we can use all kinds of vegetable oils in producing these polymers. So we're not beholden to this soybean oil, okay? We can use distillers grain corn oil, we can use corn oil, we can use flaxseed oil, rapeseed oil. Those are the more common oils over in Europe to make our monomers, okay? So then the monomers are just our feedstock molecules that we then chain together to make polymers. And then what we're really doing is we are focused in on making what we call a soft block of block copolymers. Styrene is the hard block, okay, if you will, whereas the butadiene is the soft block, okay? So we have to also think about what will the future of asphalt modification be, okay? All right. Will we face a paradigm shift? Do we have the knowledge in the asphalt industry to address our future needs? What do we believe is the time scale of changes? Okay? And when I look at how the world is evolving, and I go to different conferences, it's interesting to find out that when you get to the end of the line, kind of in the world, which New Zealand would qualify as kind of being one of those countries that's towards the end of the line for supply, they don't actually even have an asphalt refinery anymore. Australia, which is nearer to New Zealand, I think they're down to their last refinery in Australia. So whatever the refineries produce or whatever they get coming off the boats, that's the asphalt that they have. And they've got to just simply figure out how they're going to make it work, okay? If they were to try to specify PG grade, whatever, to people delivering that asphalt, they wouldn't have any asphalt. So that's increasingly becoming important for the terminal suppliers to do the formulation, okay? And I think in the United States we're down to about 60 or 61 refineries now. And over the years we're going to see the number of those refineries further consolidate, okay? And so we're going to get to a point, probably somewhat like New Zealand and Australia, that we're going to get what we get and we're going to have to figure out how to make it work, okay? Now, what do they often get at the end of the line? They're not getting soft asphalts. All the asphalts we use today, primarily, we take a PG 52 minus 34 and we'll modify it with polymer and increase its grade, okay? And so maybe it becomes a 58 minus 34E or 58 minus 34V or whatnot, right? I'm not sure that's going to be the future. The future is we're probably going to get really hard asphalt. We're going to have to figure out how to make it softer with elastic properties, okay? So I think there's going to be a paradigm shift going on here down the line because the refineries are going to be under pressure to produce more transportation fuels, taking more of the light ends out of the asphalt for those transportation fuels, and we're going to have more asphaltene-rich asphalt in the future. So how are we going to handle this? Okay, so that's a question that we need to be working on. And these things are going to be changing pretty quickly, probably in the next 5 to 10 years. It's not a generational thing. These things are already happening, and they're moving forward, okay? And so these are the challenges that I believe we have, and we've got to be aware of this, and we've got to be working on solutions. And these solutions are not going to be attained in a short time scale of 6 or 12 or 18 months. Some of these solutions take years, and it takes the development of a fair amount of knowledge to get to coming up with these solutions. Okay, so we get into polymers, okay? Now, for most people, they don't understand the polymer industry, okay? But this is just kind of a tree, if you will, a polymer tree of where we've seen that there are markets for renewable thermoplastic elastomers. We can see that as you branch out on this tree, I mean, there's literally thousands and thousands of industries and products that these materials go into. And so it's not unusual that a polymer producer will produce the same polymer that goes into the medical industry that we're going to be using in asphalt, maybe in the same production run. What's the difference between the polymer we buy that goes in the asphalt versus the polymer someone else buys to make parts that go into human bodies? It's a certification of the polymer, okay? And that's what creates the different pricing in the same polymer production run for the different industries, okay? So when we're talking about asphalt modification, again, in the polymer industry, we're kind of viewed similarly, if you will, as we are in the crude oil refining complex. Well, you guys are the lower margin opportunities, but, we do like your volumes, though, kind of perspective, all right? So when we look at this, this is some slides that Savannah Chen has put together on some of our more recent research work in here that she's been working on, okay? But the overall aspect is we want the asphalt binder modification to be used to improve the binder performance against various flexible pavement distresses. We want the polymers additives used for asphalt modification are mostly inorganic and petroleum-based, which, there are environmental and economic concerns there, okay? We looked at soybean oil because soybean oil is the most prevalently available and produced oil in the United States, all right? And like I mentioned, we're trying to look at things in an environmental aspect, but they need to be economical and they need to meet our performance expectations. We must not be willing to compromise on performance. Okay? All right. To give you an idea of the economic opportunity, we can see the butadiene price fluctuation as compared to soybean oil. Okay? Soybean oil represents a lot more stable pricing than butadiene. So if we look at that peak in the butadiene in 2008, 2009 year, that was a result of the Beijing Olympics and closing down butadiene production facilities so that the Beijing Olympics would have cleaner air. Okay? That's amazing that you can shut down butadiene production facilities around one city and the price goes up by more than 100%. That means the supply is really, really, really tight. Okay? Then we can fast forward to the 2011, 2012 years and look at those two spikes. What happened there? Those were two different instances where the butadiene facilities blew up. There were catastrophic accidents, okay? A lot of people were hurt, and people died, okay? I used soybean oil as benchmark comparison because that's the commodity price that we can easily get our hands on in terms of pricing over the years. We can use distiller grain corn oil, which actually is a lower price, has a similar pricing trend as the soybean oil, but it is about $80 to $100 per ton less expensive. Okay, so when we look at butadiene in the block copolymers that we use in asphalt, about 30 to 35% of our block copolymers are styrene, and therefore 65 to 70% of our block copolymers are from polybutadiene. Okay? So we can see that if you have the ability to have not only a lower price, but you have more consistent pricing on the feedstock for making the polymers, life is going to be more predictable, lower risk involved in this endeavor. All right. These are just some slides. June 2013 in Louisiana. I mean, you know, the guy on the left, he's running pretty hard. I don't think he does a lot of running unless there's a situation like this. But you can see what happens when you lose control at a butadiene production facility. 73 people were injured and one person died. We can look at the transport of butadiene, okay? Just the transport of butadiene itself is going to be kept under pressure or frozen. That incurs a $300 a ton transport cost. So this is where we had derailment just south of Louisville, Kentucky. Hundreds and hundreds of people had been evacuated from homes. You can see how they're trying to. This was a case where the cars were frozen. They're trying to maintain low temperature. You can see how in the forefront of the picture how is glowing orange there, and they're trying to keep control of that situation. Okay, if this had happened in an urban area, I'm sure that this would have affected many, many more people. Okay, so let's get into talking about vegetable oils. They're biodegradable, renewable, cost-effective. They're less toxic than crude petroleum-derived materials. Okay, so when we produce our monomer, which is the analog to the butadiene, we don't have to keep it sealed. We don't have to put it in a vacuum. We don't have to freeze it to transport it, okay? So we're not going to be incurring that $300 a ton transport cost, okay? What we're dealing with is vegetable oils that are composed of triglyceride molecules that consist of 3 fatty acid chains and a glycerol backbone. We're looking at those vegetable oils being able to polymerize into biopolymers with flexible and rubbery properties. We're looking at attaining those elastic properties that we're interested in, asphalt, primarily for what? Yeah, improved fatigue, improved low temperature performance. The styrene gives us the stiffer component that increases the high temperature grade, okay? The butadiene, polybutadiene component provides us with that elastic properties in those block copolymers. All right, so what are our goals? We're taking the bioadvantaged polymer, cost advantage as well, and asphalt modification. We want to do the binder characterization. We want to use polystyrene with our alternative to butadiene. We call it PESO. It's polystyrene block acrylated epoxidized soybean oil. As I mentioned before, we use the acrylated epoxidized soybean oil as a feedstock. But we've also seen that, you know, we don't necessarily even need the polystyrene for beneficial use. So we can enhance a 58 minus 28 binder and create a 64 and substantially improve its elastic properties because we're adding the rubbery component. Okay? So this is what we're targeting here and doing. Okay? So what we're doing is taking the paste cell, copolymerizing a polystyrene. We're looking at this in different molecular weights and different contents of polystyrene. Okay? And when we go to these block copolymer producers, we have to remember they are not producing a polymer that works only in asphalt. They're producing a polymer that works across a broad spectrum of block copolymer industry uses. Okay? So that's 25, 30, 35% styrene content. What we found, that's too much styrene, but we would prefer asphalt anyway. Styrene is actually more expensive than the polybutadiene and our block copolymers. So right off the bat, we're able to figure out that, we can use more of our elastic rubbery phase component in the paste cell to create our polymers. And if we want to use a block copolymer in the polystyrene, we don't need as much polystyrene either. That further economizes the block copolymers for use in asphalt. So, there's no big surprise here. We do the chemistry and chemical engineering, working on, things. You can see, and this is meant to illustrate that we start off making, when we come up with the polymers initially, years ago, we start off in little flasks where we're making grams of polymer, okay? And we're putting it through polymer testing to look at the characteristics of those polymers. And then we graduate from those grams to tens of grams. So we move from one stirring on the right there to the one on the left, okay? And then we scale it from those round bottom flasks up to 10-gallon and 50-liter reactors that are cylindrical. What I've learned in this process is that we do stuff in the lab, and round bottom flasks are perfect for reaction kinetics to occur, but we never use round bottom flasks in a chemical industry complex, full scale or pilot scale, to produce anything, okay? And so we're dealing with ideal conditions in the lab somewhat. And as we scale this up, we've got to understand how long does it take for the chemistry to take place, and what is the conversion? Are we getting to 80% conversion? Are we getting to 90 or 95? How are we getting there? Okay? And so we have to understand the scale effects of this stuff. Fortunately for us, as we've scaled up, the reaction kinetics keep getting better for us. And so that's a great advancement that we've seen with our set of technologies. We use a process called reversible addition fragmentation transfer. It's a radical polymerization process. We've worked with a few different radical polymer processes, and we found this one to be the more efficient one, and quite frankly the easier one to control in making the polymers that are of interest for us. So from the get-go, we produce these polymers. We have to do some analytical chemistry to say, are we producing the polymers that we are expecting to do well in asphalt? So we're engineering polymers to work in asphalt. We are not taking polymers off the shelf and saying, hey, will this work in asphalt? Okay? We are doing the formulations and the hard lifting and the work to understand what are the best formulations for performance and economics that will work in asphalt technology. Okay? Then when we get done with that and we verify that we've produced the polymers that we want in lab scale, and again, some of this involves the 10 or 50 gallon reactors, okay? Then we move to, let's put it in asphalt. And we put it in a range of different types of asphalt. And then we want to characterize the asphalt binder and look at that. One of the things that we use is fluorescence microscopy. So anyone that's going to be involved with polymer modified asphalt, I highly recommend you getting a fluorescence microscope, because you can take a slide of the asphalt, put it in a fluorescence microscope, and you can look at the polymer matrix. Has it developed in the asphalt, and is it there? Visually, if it's there, you've got a good network that's developed, you can see it, and you know what? It's going to perform well in all the rheology tests that take hours for us to perform. So simply sliding asphalt in under a microscope and looking at it takes us a few minutes, and we can verify that the polymer matrix there and it's developed in the asphalt. So before we get involved with even testing the asphalt with the polymers, we've got to see that that matrix is developed. Okay? So now this gets into some of the analytical chemistry, but this is not meant to make you experts in this. This is meant to illustrate that we're looking at how the chemistry is occurring with our products, how are we impacting and producing different characteristics that we know are important for use in asphalt. Okay? And so if we don't have the chemistry right on the polymers, it's fool's gold putting in an asphalt, and we know that. Okay? So this is just a highlight that we are working on. We know that the rheology, the results in the bending beam rheometer, the results in the dynamic shear rheometer are going to be highly related to the analytical chemistry that has occurred, or in some cases not occurred, in the polymers. Okay? All right. This is just a highlight that, when we do the more classic styrene butadiene polymer introduction into asphalt, that's what we get on the left, okay? And we can see that matrix, okay? When we see our polymers, we've got a different set of molecules. They're final, they're finer grained, if you will, but they're equally well dispersed into the asphalt matrix, okay? So we see in both slides here excellent polymer matrix that has been developed in the asphalt, okay? So we're very pleased. We would be very pleased with these two slides to continue on and then do binder testing on these formulations. All right. So we've done lots of different formulations. I mean, I just highlight, 17 different blends here. And what we're trying to say, I mean, we've done hundreds of different blends. So this is just part of what we've been doing here. But what we're saying is, well, the industry analog is the styrene butadiene. We take on a continuous grain, it's 54 minus 34. I think I should have been a 52 minus 34. But the net result is that between blends 1 and blend 7, all right, obviously when we did blend 1, we said, all right, what do we believe is the right formulation in this particular polymer? We blended it, and lo and behold, good. It came out close to the standard industry analog of styrene butadiene, and very close in that continuous grain range. But blend 7 is fairly, not too far off either. Okay. All right. So this is where we get into looking at some of the statistics, and we're verifying that there's a statistical difference between 20% polystyrene content versus 30, 35, and 25. Okay. And so what this is telling us is, in fact, we get enhanced high-temperature grain improvement, okay, using lower polystyrene content. So in asphalt, we're typically using 30 to 35% polystyrene, and so we're paying more for our polymers that isn't enhancing the performance of the asphalt.
What are you up to, babe? Oh, yeah.
How many people in the industry are aware of this? I bet almost none, other than the polymer science folks that have studied this in detail in asphalt. Okay. However, we do see, the polystyrene on the low temperature end does tend to provide a little bit better performance on the low end. It's about a 2, maybe 3 degree improvement on the low end, but it's about a 4 to 5 degree improvement on the high end. Okay? All right. This just looks at, black diagrams. It just highlights, if we look at this area here, we're seeing what we call this rubbery plateau going on here. And this is, again, the blend 1. And so we're getting this nice rubbery plateau. That's what we want to see, and that polymer effect in our asphalt. Okay? All right. So now we go on to these things that we call, focus groups, right? We all like focus groups, and we all want to come out with consensus, right? And, there's some really good books out there about Steve Jobs. And Steve Jobs said it's really hard to design products by focus groups. A lot of times people don't know what they want until you show it to them. Okay? That was Steve Jobs. Probably one of the best thinkers in technology in our generation, or maybe a little bit advanced, half a generation ahead of us, if you will. But unbelievable thinker. All right. So what we're now trying to do is saying, all right, we've got these different blends, there's different results. Can we come up with, statistical models that we can then use to do formulation of the polymers for use in these biopolymers for use in asphalt? And the answer is absolutely. Okay, and this just highlights that we go through, the high temperature testing, the low temperature testing, and we have different criteria, and that we can establish these different models. Okay, and that we can then use these models to say, all right, if we're going to do a formulation and modify an asphalt, what's the molecular weight of the styrene, which then drives the molecular weight of our peso, and have to have matching corresponding molecular weights that marry well together. And then we have to understand what the polystyrene content is, and therefore we know the content of the peso. Okay? And so we go through this exercise, and we take a Flint Hills 52 minus 34, and we say, what's it going to take to make this a 64 minus 28? And this is just some of the data from different amounts here. And so we come out and we say, well, basically if we want to get there, we're looking somewhere around the, we want to push that molecular weight up higher to get us to the lower temperature criteria here on the one hand. All right. But the polystyrene content's only at 5%. That's a lot lower than what we're buying in today's block copolymers that are 30 or 35%. Okay? So lo and behold, we can come up with what we call surface plots, and we can come up with what we believe is the optimum formulation. We produce the polymer, and then we blend it in the asphalt, and look, we've done a great job. Okay? Here's the 52 minus 34, continuous grade range of about 90 degrees. We use the styrene butadiene analog. Again, these are loaded in at 3% by total weight of the binder, be at 93.5. When we do our formulation here, we come out with 97. Okay? So now we've developed what industry's going to need to produce these biopolymers for use in asphalt technology. Okay, so now we're getting to the point where we are excited about this. We've walked in on the right feedstock, the right molecular weight, the right balance between the polystyrene and the bio, or what we call our biobutadiene or peso. And so what do we need to do now? Well, we want to go to mix testing. So, of course, we develop a gradation, and we're in the process of going through the mix testing, which is dynamic modulus that we can use as inputs for pavement ME, doing low temperature testing. We like the disc-shaped compact tension test, but some people advocate for the FCB, so we do both of them. We want to do the indirect tensile for moisture sensitivity. A lot of states still use that. We prefer the Hamburg, quite frankly. But again, we do a broad range of tests to make sure that we're going to have adequate performance. So we've got the mix design. We're in the process of going through that testing. So I don't have those mix tests to share with you here today. Okay? Now this was another pretty famous person that outlined, things in the scientific community. And he said, why is it that you physicists, okay, so it's kind of dating ourselves to 1940s, 50s, okay, maybe 60s. Why is it that you physicists always require so much expensive equipment? Now, the Department of Mathematics requires nothing but money for paper, pencils, and erasers. And the Department of Philosophy is better still. It doesn't even ask for erasers, okay? And that was Isaac Asimov, okay, that quoted that. All right, so we get to the point where the Center for Petroleum has licensed a lot of these different technologies, okay? And we need to scale this up from the lab to pilot scale facility. Why do we do that? We do that for two reasons. One is it de-risks the technology. Two, it provides us with more accurate information for subsequent full-scale production. Okay? And so we put in place a pilot plant. It's over $6 million, okay, in the design and the construction. And this is not like a GE toaster oven, okay? It's not like you plug it in, you turn the dial, and you want it lighter, you want it darker toast, and then, through a couple of experimentations, running toast through the toaster, you figure out where your preferred setting is. That's not what this is about here whatsoever, okay? So we had to program all the controls, which included pressure, temperature. We had to write SOPs, probably close to 100 SOPs for safety. If something happens, what do you do? All right? And so we now got to the point where we've been able to, we operate and maintain this facility by professional staff. This is not a grad student experiment, okay? And it could never be a grad student experiment, all right? This has to be done by professionals. We upgraded this last year, the facility with what we call heat tracing, so we can produce in winter operations. Now, in fairness, if it's 15, 20 below zero out and a good 30-mile-an-hour wind coming out of the northwest, we're not operating anything, okay? We generally like to operate if we're in the teens or 20s and higher and a lower wind, okay? We start off with, in this pilot plant, can we simply run water through it? And what is the flow rate of the water? Are we able to control the flow rate of water through the pilot plant? Are we able to control the temperature of the water? Okay? So we get through and we do that. We go through those exercises. And then we move to soybean oil. And we just push soybean oil through the process and handle that. So where we are, we've been able to produce the monomer and been able to attain our target characteristics. And so that's more complicated than actually then subsequently producing our PASO from the monomer. So producing our monomer as ASO, and we've been able to hit the targets. It was amazing. And by the third time we ran the facility, we were able to hit our target, and we repeated hitting the target. So we're very confident that we understand the pilot plant facility, and we can produce what we want to produce out of it to meet our needs and produce a polymer. So the next step is producing a polymer. All right. So we're working in parallel. What is the right polymer to produce? And we're in the process of verifying that through the mix test. Okay? When we're done with this, though, we're going to have a polymer. We can remove a lot of the solvent from the polymer. The polymer is suspended in the solvent, but we'll still have to send our polymer that's in a solvent to a tolling facility for that solvent removal and then what we call finishing. So that's either pelletizing or making it into crumb. So we're looking at an asphalt field trial for April, May of 2018. We believe we will be producing the polymer and stockpiling it here over the winter and being ready to go in the construction season, in next year's construction season. I do want to acknowledge a lot of entities have put monies into this, including the Iowa DOT, NCHRP, the Iowa Soybean Association, U.S. Soybean Board, National Science Foundation, U.S. Department of Ag, Iowa Board of Regents that oversees the three main institutions in the state of Iowa, and of course the licensee, which is Seneca Petroleum or Argo Genesis Chemical. Okay, and with that, I do want to recognize Eric Cochran, Naku Hernandez, Austin Holman, Michael Forrester. Those are Eric's a brilliant polymer person, one of the best in the U.S., probably the world. He got his PhD at the famous polymer research group at the University of Minnesota, and we were able to convince him to come to Iowa State. Of course, he did grow up in Iowa. So, he grew up in Minnesota over in Rochester, but he came to Iowa State for his undergrad. So we were able to convince him to come back to Iowa after he finished his PhD. Then Andy Cashone, who you guys know, he works with Flint Hills. Savannah Chen, who helped substantially in portions of this presentation. Ashley Buss has been involved with some of the stuff, more on the adhesive side. And then there's just, I probably need another slide or two to highlight all the other people that are professional staff, students, from graduate students as well as undergraduate students that have been involved in all this work. So with that, I'll say thank you and take any comments or questions people might have.
Any questions for the group? There was a lot going on there, so I can see why we have a lot. We have one question in the back. I'll walk back there, Chris, and give the microphone to Bernard.
Chris, I salute what you and your crew is doing over there. Great work. I just have just a couple questions, one probably a derivative of the other. The first one is, if these materials are biodegradable, can you say something about the stability of these materials when they are used? Stability against microbial degradation when they are in use. Are they encapsulated at that time, or do they lose their biodegradable properties? And I don't know if you want to answer that first before I ask the second question. Do I just ask the second?
Why don't you let him have that one?
Sorry?
Let him have that one.
Yeah,
Okay.
so even we think that when we buy styrene butadiene block copolymers, that we're buying purely a block copolymer, and that's actually not true. Those materials have antioxidants and other things in there to maintain their stability. So we would do the same thing and use similar analogs in our polymers as well. Okay, all of these polymers, whether they're block copolymers, the butadiene, styrene butadiene, they'll all degrade over time. Okay, so we haven't seen anything that indicates that our material would degrade at a faster rate than any other work, okay, or other polymers. Again, we're using the tests that we have to evaluate the materials. We do have plans on going. I think that when we look at in a broader context in the asphalt industry, when we look at aging, we rely on the pressure aging vessel to simulate that long-term aging. I believe that we actually need to look at something that uses UV light. Okay, and so so we're gonna use UV light to examine what happens in these things. The last thing that we want to do is produce something and then we find out that we didn't examine all these various aspects more carefully. So, we have not seen any evidence that it will degrade any differently than any other polymers out there. And I don't think that it's going to be, we're using synthetic processes just like the crude petroleum industry. I don't think that the polymers we produce are very appetizing to microbes either. Okay.
Okay. My second question borders on the model, the formulation model, which you had towards the end of your presentation.
Yes.
Why did you assume a gravimetric model? Or correct me if I'm wrong, what I saw looks like a gravimetric model. And would you not opt for some form of a physical model and rather than a phenomenological model for something of this nature?
Absolutely, we can use other models we have. I mean, we probably published. The challenge we have on this, to some degree, is its intellectual property development. We probably have close to 20, 30, patents that are either issued or under review. One of our patent applications had 12 divisions to it. Okay. So what that means is the patent office says, we don't believe you have one patent, folks. We believe you have 12 patents, okay? And so some of these things will be forthcoming, all right? A lot of information is already out there. Once the patent is published, then we publish papers related to this work. And so we have a fair number of papers that are out there. And I'd be happy to share some of those papers with folks. But we get into using not just our own standard set of rheology models, whether it's a power model or the Venus model. Of course, we used the Christensen Anderson Maristano or CAM model to develop master curves and look at the rheological behavior. We've used some other, in fact, more advanced polymer models that are not commonly considered in the asphalt industry as well. So, a statistical approach is, oversimplifies things in many respects, and I agree with you that looking at more fundamental models is an important approach and must be done as well. So.
All right. With that, we have two questions online. One is, can you use this? Can the process handle rancid soybean oil?
Yes, no problem. If we got triglyceride molecules in there, no problem. That's what we're after. It's just how we have methods that we can use to essentially filter and screen out the molecules we're interested in, and taking the molecules out that we're not interested in. So we've looked at that very aspect of things. Yeah.
All right. Another question is the bioasphalt easily aged? When do you do a PAV test?
Yeah, we've put it through PAV aging, and there's no problems. We have a wealth of data that highlights how we have to look at the reaction kinetics of the polymer in the asphalt. So we can produce various polymers that we would need to, in our world of asphalt, overheat. We'd have to react them at 210 or 215 centigrade. We know that's not viable. We need to have a reaction kinetics that are occurring in that 160 to 185 centigrade range. So we create the polymer. So first and foremost, that we get the reaction kinetics that we need in that and we generally target 180, 185 centigrade for our reaction kinetics, and then you can see the behavior and the reactivity, as you will. It's therefore not effective at the PAVH temperature of 160, 163 centigrade. Okay, so we're able to engineer these things, engineer these polymers that the reaction kinetics take place during the terminal blending at that 180, 185 centigrade, but we're not continuing those reaction kinetics in the PAV agent. Okay?
All right, with that, Chris, one other last question. We only have a couple minutes left, but you talked about field trials. I know you've done a few field trials in Iowa, and also we've been talking about possibly doing stuff up at Minroad. Do you want to just maybe a minute or two on that topic?
Yeah, so far the field trials we've done is on some of our rejuvenators. We've not done the field trials on our polymers at this stage. Okay, our rejuvenator we used twice with OMG. One was in Crawford County. It was a 30% wrap mix, local agency road. Truly, it was more like a 25% because the wrap was providing about 25% of the asphalt to the total mix. We had no problems. In fact, the contractor, OMG, got a 4% bonus based on field voids. Last week on Wednesday, we produced another mix with 30% wrap, and this was more a true 30% wrap with the binder contribution being 30% to the total mix. It was a PG58 minus 34E mix, I believe. And it was on US 18 surface with quartzite. We just got the data in from the QCQA, but rest assured it was 42 degrees and a 20-mile-an-hour wind, and we put it down. The field voids came in on average at about 6.2%. Okay, so when we're using our rejuvenator with a 30% wrap mix, we were hitting target field voids, and based on the other metrics in the pay schedule, I would suspect the contractor may in fact get a bonus for the trial run last week on US 18, which is just south of the Minnesota border. What we're looking at in the polymers is doing field trials, like we've done with our rejuvenators, and we want to put stuff in at Minroads. We want to put stuff in at the NCAT test track because we feel that those are the two preeminent facilities in the United States where people get a look, and it's the real deal. Okay, for evaluating our materials, and so it comes down to timing and how we can work with you guys at Minroads in getting this stuff done. And then it comes down to, the money aspect. We had worked out and put a proposal to a pseudo-industry governmental agency for funding. Our initial, indications were they were going to help fund the construction up there for putting in the biopolymers, and then they, because of where the soybean oil market is and the decrease in the prices, they had to cut their program back. They didn't cut our project, they just cut the size and scope of our project back. So whether those monies are going to come from, government/industry entities, that's unknown at this stage, but I think that, Seneca Petroleum is a parent company of Argogenesis. There's a good possibility they may cut the check to do it and pay and fund to do it themselves as well. Okay, so that's what I would say is what we want to do moving forward. Is that we definitely have a keen interest in doing something at Minroad.
All right. Well, thank you, Chris. I don't know if we have a virtual applause for Chris here. Hey. Again, really appreciate Chris giving this seminar. It's a new topic, new technology that I think maybe it will be something of the future to look at. So with that, next month, we're going to be talking about using wrap and chip seals and microsurfacing with Don Matthews. And so I hope you can join us for that December 19th meeting, the next third Tuesday of the month. So again, thanks to Chris and thanks for all your participation.